Hi, everyone. Welcome to the Johns Hopkins Cerebellum Seminar Series. Today, we're going to hear from a young man from MIT. His name is Federico Tessari, and Federico is a postdoctoral associate in the mechanical engineering department at MIT, where he's being mentored by Neville Hogan. He's going to be talking about synergies, this is the concept of control of behavior by the brain, not through individual muscles, but through mechanisms by which organize the low-level machinery into modules. Federico received his PhD in mechanical engineering from the Italian Institute of Technology and the Polytechnic School of Turin in Italy, where he was mentored by Matteo Lafranci. His research interests combined the design of user-centered rehab robots with the investigation of biomechanics and human motor control. He was awarded the 2024 Trainee Professional Development Award by the Society for Neuroscience and also the Best Paper Award by the IEEE IROS in the 2024 conference. So, Federico, thank you so much. Look forward to learning from you.
Thank you. Thank you, Reza. Thank you for having me here. Very happy and excited. I'll take it from here and welcome everybody. Today I'm gonna fundamentally talk about synergies, as Reza said, and this is the title of the paper we recently published, which is Explaining Human Motor Coordination via the Synergy Expansion Hypothesis. And before deep diving in the paper, let me just have a couple of slides of introduction. So as Reza said, I work in the lab of Professor Neville Hogan at MIT. We are the Newman Lab for Biomechanics and Human Rehabilitation. We are a group of about 12 between postdocs, grad students, and undergraduates. And we fundamentally work at the study of biomechanics and human motor control from a behavioral standpoint, looking at how we coordinate muscles and joints to perform motor tasks, both in the upper and lower limbs. And personally speaking, I'm Italian. I'm originally from a little village near Rome called Bracciano. And I fundamentally studied in 3 cities. I started in Rome studying mechanical engineering. Then I moved to Turin to study mechatronics. And then I joined the Italian Institute of Technologies, where I worked fundamentally in rehabilitation, robotics, and prosthetics. And I joined MIT in 2022, and I'm now currently working there on biomechanics. And my background is fundamentally starts with a lot of experience in design and control and manufacturing of robotic and mechatronic systems for rehabilitation and assistance. And you can see here some of the devices I actually worked on that span both upper and lower limb devices, as well as upper and lower limb exoskeletons. So for people with stroke survivors, spinal cord injury, amputees. And through this experience, I learned a lot about the design of these devices, but I realized that a lot of these devices were struggling to integrate well with users. And so that brought me to the questions how can we make a better job at having these devices adopted by users? And this prompted me to explore more and join the lab of Neville to learn better about human movements and how we fundamentally move and coordinate our movements, and how can that be helpful? This can be helpful to design better technologies. And so this is a very just nutshell to explain you where I come from, what's my background. So let me start by taking a step back, historically speaking. And we know that motor coordination is a big challenge to understand. And I think this question has been around for a while. And I always like to start by mentioning one of the first to question what's going on in humans. And this was Professor Woodward back at the end of the 1800s. And I always report this little passage for 2 reasons. First of all is because he made an interesting observation by looking at 4 Italians that were hand drilling back in the day. And you can see here that he spent a few hours looking at these Italians using the hand drills, and he measured about 4,000 blows. And he tried to measure what was going on, and he observed that out of 4,000 blows, there were only 1 single miss. But then he started questioning what's going on here? This is kind of a big movement. And the surface that they have to hit is very tiny. It's like the top of a nail. And he estimated that the error that they had to perform at the level of the end effector was about 1/3 of a degree. So they have to be extremely precise or accurate. And so fundamentally, he stated that even in comparatively unskilled movements, it is remarkable how many group of muscles must cooperate, and with what accuracy each must just do so and not much more. And this was a question that prompted a lot of research in the field. And I would say that another key person in this field is Bernstein, which in the 50s postulated what we can call the degrees of freedom problem, which was written in this book, like the coordination and regulation of movements. And fundamentally, the problem is that how do we find and compute and select the specific solution for a given motor task in terms of which muscles should we turn on and how much we should do so? And this is not a trivial question, and several hypotheses have been developed over the years. And you have to keep in mind that the system is, like, musculoskeletally speaking, extremely complex. We have more than 200 degrees of freedom, active joints, and more than 600 muscles, depending on how you count them. So this represents an extremely redundant or abundant space in which you can find solution. And it's not obvious which one solution you should pick from. And I think that that's prompted a lot of research over the last half a century. And here I resume some of the most prominent theories about how to explain this degrees of freedom problem. So how to find this solution. And we can see here four categories, like the equilibrium point hypothesis developed by Feldman, the motor synergies ideas developed by Emilio Bizzi and Andrea Davella, the uncontrolled manifold hypothesis, and the optimal control theory. And I'm not saying that all these theories are mutually exclusive to each other, but I would say they have been proposed to explain what's going on at the control level, what's a good descriptor of what we're seeing. And as you know by the title of my presentation, I'm particularly interested about the theory of motor synergies. But what is a motor synergy? So what is a muscle or motor synergy? Let me start by saying that most of the time, people imagine synergies as some kind of dimensionality reduction of the space. And so you use dimensionality reduction techniques such as PCA or non-negative matrix factorization, independent component analysis, to extract lower dimensional subspaces that can explain variability among many more features. And but I want also to mention that this term synergy, so this lower dimensional command, can have very different connotation depending on who you're speaking with. So if you talk with motor control expert, they will imagine synergies as a positive feature. So synergy as a control simplification tool. I have 100 features, but I use a 10-dimensional subspace to control them. So I'm simplifying control. But if you speak with stroke experts, and we have some collaboration going on in Boston, they imagine synergies as a negative behavior. So a synergy can be the flexor synergy you see in stroke survivors with hemiparesis. So the thing is that I believe that we should have more of an agnostic definition of what a synergy is. And so to me, to do so, I propose our definition, which is you can imagine synergies as any coordinated and simultaneous action of a group of features, which can be neural, muscular, or kinematic, to perform a specific motor task. So this is a synergy for me, and in this context of this presentation, this is what I'm talking about. So now, keeping in mind what's the definition of synergy, before jumping in our hypothesis, let's start taking a step back and say there's been a lot of work in extracting synergies from behavior. So fundamentally measuring EMG activity or joint kinematic activity and finding lower dimensional commands. But not as much has been done in exploring what's the nature, use, and evolution of synergies in humans. And so that's actually the three questions that I will try to answer today with my presentation. So let's say that synergies are these lower dimensional modules that we use to control our body, but is there a limit? How many synergies can humans have? And how do we reach this level of coordination? So how do we learn these modules? And how do we use them in our motor activities and motor tasks? And to answer these three questions, let's start by first decomposing human movement. And to decompose human movement, we can imagine that a given motor task, we can call it a sequence, okay? And a motor task can be decomposed in a series of temporally grouped activities, which can call chunks. This actually was a theory proposed by Lashley in the 50s and recently re-explored by Diedrichsen a couple of years ago. And the theory of motor chunks says that fundamentally you can look at every motor action in a series of chunks that are temporally grouped. And then within each chunk of movement, you can have these elementary actions, which represent the atomic level contribution to movement. And now, according to the theory we're going to present, each elementary action is a combination of two elements. And let me put here let's see the pointer so I can point it. So we have the synergy composition, which can tell you how much each feature, so each muscle or each joint, contributes to a specific motor action, and a given temporal evolution or temporal activation coefficients, which tells you how much this set of features evolve over time. And then you can fundamentally like put in chain multiple elementary actions to build a chunk and then in turn build the full motor sequence. Now, is this the only possible decomposition of human movement? I don't think so, but this kind of fits and it represents like it can represent a good portion of behavior that we observe in humans at least. So now keeping in mind this decomposition, we can look a little bit of the math, but it's not very important. You can see that fundamentally a chunk, which is this temporally grouped activity, is the summation of fundamentally a certain number of synergies that you can select that are, and as the multiplication of a synergy composition, how much each feature is contributing to a given action, times its temporal evolution. And I mean, here I put an important asterisk, like I'm assuming that the synergy composition is time invariant for that specific elementary action. And I want to mention that this is as a topic that has been debated. So it's been proposed that synergies are both time invariant versus time varying. And I tend to lean more versus the idea on the idea that synergies are a good representation when they're time invariant, because the time invariance allows this decomposition. If the synergies would be time varying, there will be no need of having a temporal evolution. Everything would be encompassed in just one quantity. And so you will lose the advantage of simplification. But I'm happy to discuss this later. So let's assume this framework and let's consider like a synergy composition that is time invariant. So now we can have these elements, the synergy composition and temporal evolutions. And so what I propose here is a framework, which I call the synergy expansion hypothesis, which is articulated in three propositions. So the mechanical proposition, which talks about how many synergies, the number of synergies, the developmental proposition, which talks about the nature of synergies, and the behavioral one, which talks about the use of these synergies. And I always leave this picture. This is actually not me, it's a friend of mine climbing in Italy. And I think it's a good example of coordination. Like climbing requires a lot of like muscular and like joint coordination. And that's why we tried to propose this for the cover image. We didn't get selected, but I still put it in the presentation because I think it's a pretty picture. Let's start by the mechanical one. And there's going to be a little bit of math here, but I'll try to make it as simple as I can. So let's imagine like that you have to plan motion for a task. And so when you have to plan motion, you typically plan motion in the world that surrounds you, the environment, which we can call the task space. And this is a space that has up to 6 dimensions, so 3 translations and 3 rotations. And you can plan motion either in terms of like trajectory, so velocity, or in terms of forces you want to generate upon the external world. But we cannot directly act upon the task space. What we can do is fundamentally control our joints. And for doing so, we move from the task space to what I call the configuration or joint space, which is like a much larger dimensional space, like more than 200 degrees of freedom, as we mentioned, which is defined by the joint angular velocities and the torques or momenta that we generate around our joints. And now the transformation between these two worlds is actually well defined by biomechanics. We have 2 transformations here that are like given by the Jacobian matrix of any kind of like physical system that fundamentally maps the joint velocities to the task space velocity and the task space forces to the joint torques. What I want you to realize is the direction of these arrows. So the direction of these arrows represent fully determined solution. So from the joint space velocity, I can get uniquely defined task space velocities. And from the task space forces, I can get uniquely defined momenta. And now, again, humans cannot directly control their joints. What they actually activate are their muscles. So we have a further level, even dimensionally larger, which is the muscle space. And the muscle space fundamentally requires another transformation that maps the joint quantities to the muscle ones, which is the muscle shortening and the tension in the muscle units. And this is also represented by another Jacobian, which is a different one that maps the fundamental, the lever arms of the muscles to the joints. And what I want you to observe is, again, in this way, that the direction of the arrows is like fully determined only in one way. And we can call these 2 different planes of planning, like motor task, the effort or flow. And I don't know which one of you are familiar with the theory of bond graph, but this actually reflects to that. So now, if we want to plant a specific trajectory or a specific physical interaction or force, we need to go from the task space variable all the way to the muscle space ones. But if we want to go in this direction, you realize that some of these arrows are pointing in the wrong direction, right? So what we need to do is fundamentally invert these arrows. And we can do so by fundamentally inverting the Jacobian matrix. But since the dimensionality of the space grows going from the task space to the muscle space, the system is no more fully determined, but is actually underdetermined with like infinitely many solutions, which are infinitely many depending, and the size of the null space is the difference between the size of the joint space and the size of the task space here, and vice versa, the size of the muscle space and the size of the joint space here. So what is this telling us? This is fundamentally telling that these underdetermined solution spaces are where we can find respectively the kinematic or muscular synergies, because some of these pathways will give you only one solution. So for example, to generate a given force on the table, my joints will have a specific amount of torque, which is going to be equal for everybody, given a certain geometry of the body. But the amount of muscle activation of my muscle, or muscle force, is not guaranteed to be the same. And so this is what I call like obligatory and selectable synergies. So the black paths are the one that will give you specific solution no matter like what you're doing. And the other ones are instead the one that will give you optional solution, the one that you can pick up depending on whatever you think is best. So the take-home message here is that the number of synergies or lower dimensional modules is determined by the size of the null space of the task you're performing, and not by the number of features, muscles, joints, or task space variables you're measuring. And this is not a trivial result, it's actually an important one. Because oftentimes, as I mentioned at the beginning, we extract synergies in the form of like dimensionality reduction techniques, like PCA or non-negative multifactorization, in which the number of synergies is limited to the number of features you're measuring. But we don't want to, we shouldn't confuse ourselves. That's just the limit of the math. It's not telling us actually what's happening at the control level. So keeping this in mind, let me just put like two additional considerations. The first one is that this framework is representative, but it's like not considering two things. The first one is that the muscle lever arms, which are encompassed in the Jacobian matrices here, are also function of the exerted force, and this doesn't report that. However, this will not change the fact that the mapping is there. So this framework is still valid. It's just simply a higher level approximation. And the second thing is that it's not guaranteed that the size of the task space is actually only 6. Because if you use multiple end effectors, so I'm using both my arms to interact with the world, the size of the task space will go from 6 to 12 because I'm moving both my arms. But this doesn't matter because it will still make this statement valid. The other aspect is instead a developmental proposition. And fundamentally, the key question here is like, how do humans go from, do humans go from coordination to individuation or vice versa? And this is an interesting question because we can look at how humans learn motor skills, especially during child development in infants. And we observe that actually there is a very stereotypical sequence on how you learn movements as a human. And this has been explored like by both Seifel and Galloway with the theory of the reflex to specialization theory, and which fundamentally says that infant starts with like this sort of like, they call it reflexive phase, with movements that are kind of stereotypical, crude coordination movements, like the grasping reflex, the stepping reflex, wall crawling, and so on and so forth. And the more they grow, the more they specialize and they go towards more refined motor skills. And the same was also done by Haders-Alger in Netherlands, which presented this theory called the neural and group selection theory, which is fundamentally telling the same thing. But I think that here the key important message, and that is the experimental observation, show that humans consistently progress from crudely coordinated and unspecialized motor actions, which we can call primordial synergies, to finely coordinated and specialized actions, we can call like generally synergies. And this is important, and it can be also easily observed in the way people develop prehension and dexterity of their hands. And this is also another couple of researchers that explored this. And when you look, for example, at the development of prehension, babies will start by moving their hand in what we call a power grasp, which is very crude movement of all the flexor of the ends. But then the more they grow, and this happens in the first months of life up to like a few years of age, you will see that they will start refining this crude coordination to more specialized movement, like a pinch grasp and then like more finger gating activities. And this is interesting to me because it seems to me that we start with this small set of hardwired coordination commands, which are substantially similar between subjects. And then we slowly expand our like set of commands and specialize towards a large set of learnable coordination commands, which are not guaranteed, and this is the important part, to converge to the same solution. So it seems that we all start with the same starting point, but then we're not guaranteed to converge to the same solution for a given motor task. And I mean, there are some observation. Now, I'm telling you there is this specialization, but how much can we specialize in our movements? I think that the ideal upper limit is individual motor or joint action, so individual muscle activation or individual joint movements, I don't know, elbow flexion. But this specialization, I think, has a biomechanical limit in the sense that some coordination patterns are actually not a consequence of neural control, but biomechanics. I cannot bend my knee backwards or without like breaking my knee. And so biomechanical constraints like ligaments and tendons can produce some kind of coordination that is not represented by neural activity. But I think a portion of that instead is actually like driven by neural control. And it's interesting that this framework, this expansion of commands, can also be looked in the opposite direction. And this is more of a speculation, but that I'm interested to explore, which is the idea that, for example, neural damage to stroke might induce a regression back towards a lower level of quality of synergy, so more crude, undesired coordination patterns. Imagine the flexor synergy of a hemiparetic patient. And so this could be an interesting framework to explore how we go from like small set of hardwired coordination commands to highly specialized ones. The last topic and the last point of this framework is the behavioral proposition. So like we said that we have this growing set of commands that we can learn, and that this is not limited by the number of features we're controlling, but just by the size of the null space. So then we can imagine that there is some kind of library where we store these commands. So we store this synergy composition, which is how much we activate each feature, and we fundamentally build a library of these commands that we can fundamentally pick from. And the same goes for the synergy evolution. So how much we have to activate over time these features, these specific features. And so the job of generating a motor command, so a motor generating an elementary action, would fundamentally become a job of selecting the best synergy composition and combine that to a temporal evolution to generate our motor chunk or our temporally grouped motor activities. And this could be either at the kinematic level, so joint activities, or at the muscular level, so like muscular activity and force generation. So keeping this in mind, I want to stress that the idea is fundamentally that learned synergies are stored somewhere and recruited upon need through what I call a select and shoot strategy. And I want to stress that there is actually some work looking at the neural basis of these synergies. And I highly recommend this recent review by Victor Cheung and Seki that wrote an extensive review about, the neural basis of motor synergies, which I think it talks about where actually these synergies might actually be stored in the central nervous system. And we can discuss this maybe during the second part of the presentation. And fundamentally, the key question is like the synthesis of synergy evolution is an open question. So how do we generate this temporal activation? And I mean, there's many theories. Definitely one is that of these unimodal bell-shaped velocity profiles, which has been found in many point-to-point reaching movements, and like talk about these smooth trajectories of like unimodal split profiles. But the other thing I want to mention, and I think it's important on this slide, is what I'm presenting here is a much feed-forward looking strategy. So like picking and shooting out. But I'm not claiming that feedback doesn't happen. And I mean, like, it would be like naive to assume that feedback is not there. Actually, feedback is there, but the feedback is there upon need. I think that with the neural delays that we see and observe in our system, I think that a lot of the system relies on predictive control and establishing something that can use and rely on upon like, and then correct only upon need. So keeping in mind what I presented now, I want to give you two examples of how this framework could be used and what like we find confirmation of the result. And I will first give you a numerical example, and then I will give you an experimental results that you can look at. So as a numerical example, the question that we asked is, can we actually find evidence of multiple behaviors, of multiple selective rule synergies emerging from exactly the same motor task, that starting from the same learning point, so the same common primordial synergy. And so fundamentally here, the goal is to demonstrate the first two propositions of the hypothesis. So can we find multiple synergies for the same motor task, and can these synergies be diverse despite starting from the same point? And to do so, we used like a real case scenario of generating a constant and effector force. So imagine this model, and this is like a very simple 3 degrees of freedom link model, representing planar movement of the arm. This is the shoulder, elbow, and wrist, and this is the end effector of the end. And it's like actuated by 10 different tensile units representing our muscles. And you can see we have both monoarticular and biarticular muscles. And the idea is fundamentally train this model to generate a constant force in isometric conditions, so push fundamentally in a given position. And I mean, there is some math here, but we're not going to jump into math. But going back to the structure I presented before, we're fundamentally here. So we want to generate a given force. To do so, we need to generate some momenta, and these are fully determined. So there's not going to be any percent of selectable synergies. But then when we map from the momenta to the muscle forces, here is where we can find actually diversity and like expansion of possible solutions. And to do so, you have to do some math, but this is not very relevant for today, so I'll skip that. But the only equation that you read to matter is like here is where you see the redundancy of the system coming up in the inversion of this relation here. And in this case, since we have a two-dimensional space, we're moving in the plane, we have three-dimensional joint space because we have three fundamental joints to move, and we have a 10-dimensional muscle space. So the system has a 7-dimensional redundant space in which you can find solutions for your motor task. So here you can see the same model used to generate multiple forces in multiple directions. And the fundamental goal here is to fundamentally minimize the difference between the torque that is required by the biomechanics of the given configuration with the multiple possibilities that you have with your muscle forces. And so this problem can be cast as fundamentally a minimization or optimization of an error, okay, which in this case has been modeled as the sum of the squares of the difference in torques. And the square is important because you don't want the terms to cancel each other. So you want that to be a minimization. But it's important to stress that we don't want to set a very tight constraint. We want to set something that we can call a good enough constraint that will converge, but we're not looking for a specific like optimum. We want to look for multiple solutions to the same solution, to the same task. And to do this, we use like a method which is stochastic gradient descent. You might be familiar with it. And we had all these different rollouts of this algorithm start with the same primordial synergy. So all the muscle starts at rest without generating force, and then they can explore the solution space, the 7-dimensional redundant solution space, to fundamentally like reduce the error to a certain threshold. And in this case, we set the threshold to like 0.01 square Newton meters squared. And what are you going to see now is the results of the generation of a specific force. In the paper, there are multiple, but I'm going to show only one here. So you want to generate, for example, 9 newtons of force in this direction. And as I told you, the torque that you need to generate is given, is obligatory by biomechanics. But then like you can start like training this stochastic gradient descent to generate multiple solutions. And we generated 51 solutions. 50 are actually generated with the stochastic gradient descent, and one is actually generated with the least square solution. So it's an optimal solution. And what you can see here is how much the error decreases with the iterations. And we can see two things. The first thing is that the solutions, different solutions, converge pretty quickly with a slightly different number of iterations. But in 20 iterations, you're fundamentally like around zero error. And the other thing is that I want to mention is that it's important here to stress that we're not looking for optimal control, but for good enough solutions. And I recommend like looking at this paper by Jerry Loeb, which is called optimal control isn't good enough. The title is a little bit funny, but it's very interesting and like tells the point that we shouldn't look for always optimal solution, but a good enough might be more representative of actually what humans do. But now the question is that we were able to generate like more solutions, so 50 solutions, compared to the number of the features we're controlling, so 10 muscles. So now, how are these solutions similar to each other? To measure this, fundamentally what we did is compute a metric that is called DM, dimension insensitive Euclidean metric, which, like long story short, is a more nuanced version of the Euclidean distance. And we prefer to use this, and we have a paper on this, that compared to cosine similarity, because we've shown that in the cosine similarity tends to be very sensitive to high-dimensional quantities. And so we wanted to avoid any bias due to that. And like I want to mention how to interpret the plots that are coming up. So you should interpret DM with the fact that lower values of DM mean like higher similarity, higher values of DM mean lower similarity, and a DM of 0 means that the quantities you are comparing are indistinguishable from random comparisons. So like imagine that you're going to have a 0 value, and then the more you go towards the negative values, the more you are going to have similar things. The more you go to higher values, the more you have dissimilar things. So in total, we have 51 synergies that we generated, and we compared them all across each other. So we have like about 1,300 comparisons. And to show them, like we have an histogram. So here what you can see is the DM computed across all the synergies we've generated. And here you can see the dashed line represents identical, random, or orthogonal synergies. And you can see a distribution is like presenting like almost unimodal with this little tail here between identical and random. So there is diversity, and we can actually see that by looking at specific cases of this histogram. So here you can see the most similar synergies, and here are the activities of the 10 muscles, and you can see they're pretty much the same. But then, like, if you look at the mode of this distribution, you can see that actually this is most of the synergies we generate. They're actually very diverse with each other. You can see that like different solutions are generating different muscular co-activations. And now you have also like extremely different ones, like towards the high level. But what is this telling us? So fundamentally, these 51 selectable synergies assume very different variables, despite all starting from the same point and all generating a successful like force at the end effector. And you can imagine these selectable synergies to be the learning patterns of individual subjects. So every subject could have like chose a different path to converge to the same actual output behavior. And this is because we have redundancy, and the system allows for the emergence of this variability. And so wrapping up, what are the take-home messages here? The first one is that we were able to generate multiple synergies to accomplish the same motor task, and these were much more than the number of control features. And the second is that these synergies were generated starting from the same primordial synergy, so from the same starting point. So the idea that you can actually find multiple solutions and variability across subjects that is not just noise, is actually different motor solutions. And so I want to wrap up, and I think we are right on time, with like some actual experimental result that fundamentally try to show the same thing. So we did this experiment back in the day with the University of Pittsburgh, which was developed to study the physical interaction and was designed to be a challenging physical interaction task. So a ballistic release task. So subjects were tasked to push against the load and maintain that force for an unknown amount of time. Then the force would be released and they have to converge in a specific position in a very short amount of time. And the original purpose of this experiment was to study the human predictive control of physical interaction. So we wanted them to fundamentally like do some kind of stiffness modulation. So set a stiffness and an equilibrium position, and when the load is released, they rapidly converge to that point. But here, what we're asking is, can we find evidence in this specific task of a synergistic control of muscles? And this can tell us if there is evidence of control simplification. And at the same time, do different individuals, we have multiple subjects, employ different muscular coordination strategies to perform the same motor task. So fundamentally showing that despite having a given set amount of muscles, we can go beyond the number of features we have. And also another question that is not for today, how this is related with stiffness modulation. And what I'm going to show is partly reported in this paper that is mentioned here, but also some results are like currently under publication. So you're not going to find them online, but I will present them today. So just to mention like some of the experimental details, subject have to generate different level of force. They have to like move at different distances. And the task looked like this. So they have to have a force ramp phase, then to have to hold the force for an unknown amount of time that could vary. Then the force is released and they have to move to a certain target within like 500 milliseconds. So it was a very rapid movement that they have to do like without corrective actions. And we sampled muscle activities from many different muscle groups. So the flexors and extensor of like the wrist, of the elbow, and then the deltoid anteriors and posteriors and trapezius and pectoralis. And so the key question is here, okay, is there evidence of coordinated activity of these muscles? And how can we study that? Here you can see the stereotypical subject and the activity of one of the muscles in one condition. And you can see that the activity is characterized by three phases. During the force hold, there is a constant electromyographic activity. During the release, there is a spike, potentially due to the reflexive action. And then there is a slow decay during the movement towards another steady state value during the position hold when they reach the position. And this was actually like, this behavior is very stereotypical. Here you see 9 trials and the trial average. And this behavior we observed it was consistent across muscle, subject, trials, and all the different conditions we tested. And the quick question we had is like, is there an easy way to capture this behavior across all muscles? And what we did is non-negative matrix factorization. I'm not going to enter in the details of the math here, but fundamentally what we wanted to do is like a division of the matrix that contains the data of all DMGs organized by columns, and like this, like split them between like a time invariant feature activation, so how much is muscle is contributing to the movement, and a temporal evolution, so how much each of the synergies evolves over time. And what I want to show here is the result of this like non-negative matrix factorization. And we have 2 key plots here. The first one shows the amount of variance that is like represented by each synergy. So you can see that already the first synergy accounts for more than 80% of the variance. And with two synergies, and we have almost 90%. So fundamentally, what we observe is that the first coordination pattern, the first synergy, fundamentally represents most of the data. And the other strikingly interesting thing to me is that the first coordination pattern has a strikingly similar behavior across all subjects, so a common temporal evolution. So the synergy evolved to time in the same way. So there is the idea that fundamentally there's a common and lower dimensional neural command that is shared across simple muscles, seems to be like well represented by the data we collected. However, the question that remains open is that, okay, this is telling you how the first synergy is evolving over time, but are subjects recruiting the muscles in the same way or in different ways? And to do so, we fundamentally we performed the analysis that we performed for the numerical example. So we computed the similarity between synergies. So first of all, what I want to remember is that it seems that muscle synergies as a control simplification tool are actually good in this case. So with one coordination pattern, we can represent most of what we see across 8 muscles. And so what you see here is the diversity of the synergies between subjects in both the force pushing phase and the position hold phase. This is the force hold phase. So you can see again the DM metric, and you can see that this is the muscle activation compared across subjects for the first coordination pattern. And you can see that again, they're not identical, and they present very diverse activations depending on the mode. If you look here, we have the way they activate their 8 muscle changes quite a bit. And the same is true for the position also. Also, when they reach the final goal of their movement, they have also a wide variability across subjects. And this is interesting. Here I'm showing the same histograms, but comparing between and within subjects. So within subjects are the blue histograms, and between subjects are the red histograms. And what you see here is that within subject, there is also some similarity, some dissimilarity, but it's much less than between subjects. So these two curves, the red one is always to the right of the blue one. And this is telling us that within subject, they tend to stick to the same solution, while between subjects, it's not guaranteed that the solution is the same. So fundamentally, what is this telling us? It's telling us that the observed behavior, first of all, could be well described by one coordination pattern, which you extract with non-negative metric visualization. And this is a strikingly similar time course across subjects. And so despite this common time course, we found that each subject employed a different combination of muscle activation, which we can call selectable synergies, to generate the same output behavior. So in other words, each of them recruited the 8 muscle that we analyzed in different ways, but activated them over time in a remarkably similar way. And so this is, I think, is in line with the framework I presented, and especially with the fact that we can have more solutions in terms of muscle activation than the number of features we are controlling. But at the same time, those are activated maybe because driven by the task, if they evolved over time in a similar way. And also it argues for the concept of time invariant synergy. So we have a very well consistent temporal evolution, but very diverse muscle activations. So wrapping up, and this is more like points that we can discuss later. In the idea we're presenting here is that the motor synergies, and I think is agreed with other people working on this, are the building blocks of human motor control. And they emerge as a natural consequence of the abundance or redundance of our musculoskeletal system. And the synergies appear in humans starting from crudely coordinated motor patterns, which we call primordial synergies, and continually expand to highly specialized actions. And those synergies are stored and evoked, and fundamentally follows the theories of motor learning and adaptation to fundamentally activate these muscles. And I think that this framework could have applications and impact for different fields. First of all, for modern neuroscience, I think this could be a useful framework to investigate human motor coordination and maybe find new answers to this Bernstein degrees of freedom problem. And it can also have impact for rehabilitation in the sense that it might be a way to bridge the conversation between people that study synergies as a negative effect of stroke impairment and people that study synergies as a useful tool to simplify control. And last but not least, and this is my personal interest, I believe that this framework could also be used to design better biomimetic control strategies to simplify robot control. So that's it. I want to acknowledge the lab that funded this research. All the data is actually available and you can find it online, and I'm happy to share it. And there's no competing interested. This is my contact if you need to reach out to me, but I'm here. And I'm happy to take any questions.
Wonderful. Federico, thank you so much. And if you have any questions, just go ahead and raise your hand and I'll call on you. And there were lots of interesting stuff that you presented. And I guess if I want to go back, I want to start thinking about the math that you described, where you went from a 3-degree of freedom system that wanted to produce an endpoint force, and you described how, well, that system with the many muscles, there are ways to find the torques that you need to produce at each joint and the muscle forces that you need to produce. I wonder, in that system, you didn't describe the concept of a synergy here in this specific task. So if you wanted to do the experiment that you described in humans, in your math, you would maybe go from a force from 0 to something, maybe you'd be some noise there, and then maybe you'd then ask, if you apply the same non-negative matrix factorization to this system, where the EMGs and what have you, you would get something. And I wonder if you want to tell us a little bit about that kind of a thought experiment.
Sure. So the idea is that in this case, what I think, and please correct me if I understood the question wrong. The idea is that we haven't directly extracted synergies using negative matrix factorization, but it's because in this case, it will become extremely trivial for the specific model we use right now, because it's a very simple pushing task with no movement involved. And so in this case, we did perform no negative matrix factorization on the signals, on the measured and modeled signals of the muscles, but the result was exactly the same as looking directly at the activation of a muscle, because there wasn't a dynamic component. Of course, introducing a dynamic component, as you have seen in the experiment, calls for the use of dimensionality reduction technique, but this was a simplification. We can definitely model also the dynamics. So the model is there, but we haven't include this in the work, but it's definitely in the pipeline of what we want to do. And I want to mention that noise was included in the system. So in the equations you see here, there is no noise because I wanted to present the ideal equation. But in the learning process, we introduced noise to model effectively the fact that the system is noisy, and is noisy at the level of each muscle as well as at the level of the joints. I don't know if this replies to your question, Reza.
Yeah, that's fine. Yeah.
Yes, please.
So in the units, were there any mechanisms that those experiments went to fatigue or to muscle failure? Was there any sort of mechanism that the participants relied on, but did it convert at all to some fatigue mechanism?
Yeah, sure. I don't know if they heard the question from
Repeat it.
Yes. So the question that she asked is was there any evidence in the experimental data of fatigue or specific strategies that the subject relied on that could explain something that you see? And the experiment, as I mentioned briefly, and let me go to just this slide here. The experiment was designed to be very challenging. And actually there was both a learning phase and we tried to compensate for fatigue because the experiment was very long. So in the results I report here are after the learning phase. So we wanted to look at results without looking at the learning of this strategy to have some consistency across trials. And for fatigue, the way we tried to minimize it was subject that could take as many breaks as they can. And we fundamentally monitored that the EMG was not presenting any variations over time within the same subjects. And at the end, after many tuning of the experimental paradigm, we managed to keep the level of fatigue pretty much constant. So we didn't see much of that. I think that the strategy that they mostly relied on in this experiment was really trying to preset their stiffness, especially that elbow and shoulder and wrist, to fundamentally converge to this position. Because as I mentioned here, the movement happened very quickly. So they had only 500 milliseconds. And we enforced very tight success conditions. So they had to maintain this position without performing adaptations. So the only way in which they could fundamentally perform this task was in a very predictive way. So before the release happened, they had to fundamentally preset their joint stiffness to converge when the release was dropped. And we believe that this was the strategy they used. You're welcome.
So you mentioned that you thought the synergies lived in the central nervous system, right? Earlier, is what gives cause for thinking that they're there and not in like higher order brain centers, and if they do live in the central nervous system, what leads you to that like line of thinking?
So the question I was asked is, do synergies sit? Where do synergies sit at the neural level, or do they sit at the central nervous system level, or in any other like neural structure? And my answer to this is that the results I present do not show where they sit, these synergies, and I want to be clear about this. But there is literature investigating at the neural basis of synergies, and that's why I mentioned that review by Victor Cheung and Seki, because in their review they claim that actually there is not one single point in which synergies might be located, and there is some evidence that there are both spinal circuits that elicit some of these synergies. For example, locomotor synergies for the lower limbs. There is good evidence of spinal circuits that fundamentally elicit this, and there has been like seminal works on cats where there was the connection between the cerebrated cats, in which you can still see the evidence of this synergistic pattern of the lower limbs. But there is also evidence that there are higher order, like nervous level, cortical, for example, or brainstem that can contribute, the sending commands that can contribute to the activation of synergies, especially for more complex commands. Or even actually, there was some recent work looking at what actually posture could be looked as a synergy. So how to maintain upright posture. And it seems that upright posture has some higher cortical influence than locomotion. So for example, there is some works mentioned in Cheung and Seki review that they claim that they looked at the fact that when you look at the corticated or the cerebrated, I don't remember, cats, they could maintain locomotion, but they couldn't maintain posture. So that indicates that there is a higher cortical contribution to the control of posture. And I think there's multiple circuits, and I don't want to claim which one is the one. Definitely, for some circuits, spinal is sufficient, but for other motor commands, cortical activity might be needed. You're welcome.
Thank you for that. So we have a question. Ali, go ahead.
Hey guys, thank you, Federico, for the very interesting talk and very interesting framework, certainly. My question is about like what is the synergy in its core, and when can we tell whether some coordination pattern is a synergy or not? So for example, when you do a non-negative matrix factorization or like PCA, and you get some really like good explanatory coordination patterns that can explain 80%, 90% of the variance, could you call them at that moment a synergy, or that could also be represented in the motor cortex or in the spinal cord? Or should you also, like, for example, go to your model and then test some things and get the Jacobians and then look at all the possible coordination patterns and then possibly call that specific pattern that you got from PCA or NMF a synergy? Like, when we call it a synergy, is it simply a methodological term that we want to like call, we want to extract, or is it something else? Is it like when you say it is the result of the NMF, and then when you also say the brain could be using, or we could be using it as a building block of the movement, what is the moment that we can conclude that conclusion, or what is the result that we can see to make that conclusion? Thank you.
Okay, thank you for the question, Lee. And I think that you raise an important question. So I think when you perform the non-negative metric factorization on any form of dimensionality reduction, what you're getting is a descriptor of the data you're analyzing. And I think you are intrinsically limited by the math you're using. So for example, in the case of this data, and let me go back to this slide, one sec. So what we see here in this slide is that, like, with this method, the non-negative matrix factorization, we could see that like most of the variance could be described by 1 to 2 synergies. And so this is just a descriptor. I don't think that this is like telling anything about the neural circuitry in this specific experiment. At the same time, it's a good descriptor, and so it can help us to build an hypothesis that then needs to be checked somehow. So in this case, we haven't looked here at any neural activity, but there is work that looks at the neural basis of this and claims that this coordination, this level of simplification that we see through this mathematical tool can be confirmed by actually like neural measurements. And especially like there was evidence of this simplification and this control dimensionality reduction in premotor neurons in the spinal cord. And so fundamentally, like the hypothesis is that cortical level project to this premotor neuron circuits that then like in turn project to multiple muscle and motor neurons on muscle units. And so that's actually where the synergy would sit. To me, especially like personally speaking, synergies are and this framework is a very good descriptor that can be used to simplify control, especially looking more at as an application eye. So like, can we use this framework to simplify the control of devices that we want to give to users for when you have actually motor impairments? So like prosthetic devices, exoskeletons, assistive devices. And could this be a framework that could help people have a better user interaction and a better agency over these devices? So I think that the representation is dual. On one hand, we have a good descriptive model that could be used to simplify control of devices. On the other hand, I think this could be a good framework to explore how coordination is solved neurally. And I think that requires more research from a neurophysiological standpoint. I hope this replies to your question, Ali.
Julia, go ahead. You have your hand up.
Hi, I had a question. So it's very interesting you see that diversity of solutions for different synergies. And I was curious how much you thought that was kind of driven by the fact that from a feed-forward standpoint, you could choose a number of solutions, but alternatively, what if feedback is limited or difficult? And so like how, like say for example, you had to learn that task in a certain way where you used a certain number of muscles, how limited people would be in their ability to set, say, a specific coordination pattern, and from a feedback standpoint, know that they're actually executing things in a certain way. If that makes sense?
I'll try to see if I understood correctly, Julia. So your question is, if I understand correctly, and please let me know, is how could you explain that variability you see in possible muscle activation patterns and how much that will be mediated by feedback? Is that what you're aiming to?
Yeah, I guess so. If you had to learn that same task, but you actually, in order to get a successful trial, you had to activate a specific type of coordination, how successful would people actually be at that? Can they learn to activate specific muscles similar to each other? And is this like a feedback limited situation?
Oh, okay, I see. I think that in this specific task, definitely like there was quite a variability in success rate, and that might influence also the kind of solution you chose. And I think that the constraints on the solution space come from very different factors. First of all, there are task constraints. So like the fact that they had to reach that specific position in a certain amount of time and don't perform corrections. The other, they come actually from their biomechanical structure and anthropometrical physical structure that will fundamentally like push one subject with respect to another to lean more on one muscle or the other. And I think in that case, there is a combination of multiple factors. I want to mention that the variability in subjects, and this is something interesting, tends to reduce the more you try to specialize more. And I always mention the example of professional athletes or sport. In the case of athletic movements, if you look at like naive players performing a specific like sport activity, like for example, shooting a basketball, if you take 10 naive players, you will see a huge diversity in the way they shoot the ball and in the way they activate their muscles to perform that action. If you take 10 NBA players, what you see is that this variability collapses because in this case, they have been exploring more than solution space, and they're looking more not just for a good enough solution, but for something that might be closer to a local or global minimum. So I think that a lot matters on how much you care about the task in terms of like which kind of performance you want to get. And I do think that a lot of the time when humans perform movements, they don't care about a perfect optimum, but what I call and has been called as a good enough solution. But in some activities, you need eye specialization and eye quality movements. And in that case, I think the variability reduces because you are over-constraining your task. And in that case, the solution might be more limited and so more similar to each other.
Wonderful. Thank you, Julia. Are there any other questions? All right. Thank you, everybody.
Thank you.